Okay, so we're going to talk about symmetry here. Symmetry is when, what we kind of know it as is just being the same on both sides. So you could draw a line of symmetry and fold a figure onto itself, and it would be symmetrical because it would map the figure onto itself. Mapping the figure onto itself is more of the mathematical definition. We have three types of symmetry we're going to explore. We're going to explore reflectional symmetry, so drawing a line of reflection and mapping the figure onto itself. Rotational symmetry, so rotating the figure and getting it back to itself, and point symmetry. Point symmetry is a special type of rotational symmetry where a rotation of 180 degrees exactly maps the figure onto itself. So some figures will have all three of these, and some figures may have one or two, and some figures may have 0 types of symmetry. Those are called asymmetrical. So if we look at this figure and we explore reflectional symmetry, this particular figure has 2 types of reflectional symmetry. I can take and draw a line through the center horizontally of this figure like this. And this figure would be the same on both sides if I were to fold it in half. I could reflect this figure about this particular line and the figure would stay the same. So if I took all of these x and y values, and remember when we do a reflection we change the y value. So if I took this one and changed the y value, it would map itself on to another point on the picture. So that would be reflectional symmetry. I could also do a reflectional symmetry about the y. So I could do a vertical line through the center, and again I would reflect across this line. If I reflected this image across this line, this time I'd be changing the x values. So this x would change over to this x. And so when I flipped them, or when I changed those x values, I would map the figure right back onto itself. Now this figure also has rotational symmetry. So if I take this figure and I twist it around, now that would be a 90-degree rotation. It doesn't map onto the original figure. So remember, the original figure is this one right here. That's what I'm trying to get back to. However, if I continue around 180 degrees, bam, I am right back on to that exact same figure. So this would also have rotational symmetry. Rotational symmetry can be a number of degrees. So it could be a 90-degree rotation, like a square would have rotational symmetry of 90 degrees. It can be 180, 270, or any other specific rotational symmetry number we can think of. If it's exactly 180 like this guy would have point symmetry. So it would be a rotational symmetry of 180 degrees around a point to map it back onto itself. So now we're going to look at different lines of symmetry. So this question says, how many lines of symmetry does a regular hexagon have? So we have to understand what the word regular hexagon means. You know what a hexagon is. It has 6 sides. Regular means that all of the sides are the same length. So if I were to measure, each of these would be congruent. Not only that, but so are all of the angles. The angles here all measure exactly the same. That's the definition of a regular hexagon. It's important to know that we're talking about a regular hexagon, because I can draw a hexagon that is not regular and it has different lines of symmetry. So if I were to draw this hexagon without all congruent sides or congruent angles, my symmetry would be off. Okay, so there's a picture of a hexagon. Still has 6 sides, 1, 2, 3, 4, 5, 6, but I don't even know if any of those sides are congruent. When I draw these lines of symmetry, it's going to be different than my regular hexagon. So that word regular is really important here. Okay, so let's draw some lines of symmetry. I can draw lines of symmetry through each vertex. The vertex is where the 2 lines come together to form the angle. So I could draw lines of symmetry through that vertex. That would be 1. I could go through to the next vertex. That would be 2. And then I could go to the next vertex. That would be 3. So right there we've got 3 lines of symmetry. So there's a nice pretty picture of those first 3 lines of symmetry. Now I could also go through the midpoint of each opposite side. So I could go this way. That's 1. That's 2. and that's 3. Again, those lines of symmetry would map the figure onto itself. So I have 3 more lines of symmetry. Now in total, I have 6. All right, so there's another pretty picture. Now if I put both of these together, that would mean that I would have a total of 6 lines of symmetry. Let me show you a picture of all of those put together. Check that out. Now we could count all of those lines of symmetry. We've already done it. We know the answer is 6, but we could count 1, 2, 3, 4, 5, 6. This guy right here is just this same line. This guy right here is this same line. So we don't want to continue around. So that would be 6 lines of symmetry. Okay, so this one we're going to do angles of rotation that maps the figure onto itself. So before I start cutting and pasting some pictures in here to show you actual angles of rotation, I'm going to see if this will work. We're going to rotate this figure around. So I have an image on the back, and what I'm going to do is show you a rotation. Remember, rotations go counterclockwise, so we're going to go this direction. And I turn it about here, and it's still not mapping onto itself. So I'm going to keep going and going and going and going, and oh, it looks like right about there would be a map onto itself. So we already rotated past the 90 degree, and what we're really looking for here is what is this angle of rotation. Okay, that angle of rotation is 120 degrees. Now I can keep going and continue to rotate. So I can keep this one going and continue to rotate. There would be 180. You can see my line straight up and down. And then I'm going to keep going, and it's going to go another angle measure to get it back over here. That guy's going to be 240 degrees. Okay, so now we've got a rotation of 120 degrees, and we've got a rotation of 240 degrees. Okay, I know you're thinking, but can't I keep going? Ms. Zender, if I kept going, wouldn't I get back to it again? Yes, that would be a 360 degree rotation. Every single figure has a 360 degree rotational symmetry. So we really don't worry too much about that one. So this one would have 2 angles of rotational symmetry. It would be 120 degrees and 240 degrees. Okay, so now we're going to look at a figure and determine the types of symmetry the figure has. So this one looks like it's a flower petal. It looks like it's regular, although in reality, flower petals are probably not completely regular. But we're going to assume, for the sake of this particular problem, that this is a regular flower petal. Now, if I were to start drawing lines of symmetry, drawing lines of reflection, I could draw 5 different lines of reflection through this one that would map the figure back onto itself. So I could draw them through each of the, let's call them vertices, or the edges of the flower petal. So I could go here. I could do another one through the next line of the flower petal, if I draw it correctly. Okay, so I could continue to draw these lines of reflection and create 5 lines of reflection. I've got a better picture. Hold on just a sec. All right, that one looks a lot better. So those are my lines of reflection. So I could reflect those points, fold them in half, and it would create the same picture on both sides. Okay, now I'm going to try and show rotational symmetry here. At each of these lines of reflection, I could rotate the figure around. I'll try to make it smaller so we can see. Okay, so that one doesn't work. I can go all the way to this one, and look, I've mapped my figure onto itself. Okay, so I have rotational symmetry, but it's not point symmetry because it's not 180 degrees, but I do have 5 different rotations that I can make so long as I take the petal and map it onto the next petal. So since this figure I'm going to assume to be a regular figure, what I can actually do here is I can take its 360 degrees of rotation in one circle, and there are 5 points here. And so I do 360 degrees divided by 5, and I get a rotational symmetry every 72 degrees. So multiples of 72. So I could get 72 degrees. I could also get 144 degrees times 2, 216 degrees, and 288 degrees. So that gives me 5 lines of symmetry with rotational symmetry for 72, 144, 216, and 288. So when I map it back onto itself for that last one, that 5th rotation, that's a 360-degree rotation, and we said we don't count that one. So this symmetry, this figure has reflectional symmetry as well as rotational symmetry.